Okay, so let's go through some examples of reductions, and we're going to go through one that's particularly famous. So we're going to go through the independent sets problem and the clique problem. Okay, and what's useful about these problems is that the two are basically mirror images of each other. So hopefully these will be a good vehicle for us to show how to do reductions. Okay, so um, let's say we are given a graph and a set of given a graph G and a set of vertices V. And so we define an independent set as the set of vertices if no two vertices in this subset of vertices are connected by an edge in the original graph. And we define a clique, the subset of vertices V prime, as every pair of vertices in the subset is connected by an edge of G. Okay. So, for instance, in this graph right here, this would be an independent set, and this would be a clique. Okay. So, so let's define the two corresponding problems. First, independent set. Independent set problem. You're given a graph G and an integer K. Does G have an independent set that is greater than or equal to K? Remember, we have to formulate these problems as decision problems. So we need to basically show, we need to make the output yes or no. So how do we do that? Instead of saying what's the largest independent set or what's the smallest independent set would be pretty obvious. It would be 1 or 0 if you're allowing for yourself for that. But instead of saying what's the largest independent set, you say does the independent set have a size greater than or equal to K? Okay? And then if you want to know the largest independent set, you could vary the size of K. Okay? So, is this problem easy or hard? Right? That's what we want to know. And if this problem is easy, if there is a polynomial time problem for this, then it's trivial. You'll just have to increase the polynomial time by a factor of k to find the largest possible independent set. Okay, so reformulating the problem as a decision problem doesn't necessarily impact the difficulty of the problem that greatly. Okay. Correspondent. On the other hand, we define the clique problem as if there is a graph G and an integer K, does G have a clique of size greater than or equal to K? Okay, so notice that these two problems both have the same input, so it will hopefully make our reduction simpler because they both take in a graph and a particular integer. In the next lecture, we're going to go through problems that take in different types of input entirely, right? But since this is our first reduction, let's keep things easy. Okay. So, recall, decision problem. The reduction from x to y is simply an algorithm that takes a input x, an instance of x as an input, and outputs an instance of y as an output, such that if x is a yes instance, y is also a yes instance. If ix is a no instance, then iy has to be a no instance. Okay, so a independent set. So how do we do that? How do we turn? So what we want to do, remember the reduction diagram. We want a y, iy, ix, yes, no. Okay, this is what this is saying. Okay, so with regards to the independent set / clique problems, how are the two related? How is ix and iy related? How could we turn a yes instance of an independent set into a yes instance of the clique problem, and vice versa. What is the relationship between the two? That's what we need to know. So let's look at the independent set right here. Seems pretty nice, but as you could tell, things are drawn peculiarly. So the independent set in this case would be, what's the largest independent set we could get? We got this, we got this, this, this. Oh no, not that. That's, that, not that, not that, not that, not that. I think we got to move that there. I think this might be, oh, and we got that. There we go. So we could get an independent set of size 4, possibly greater. We'll check. So what does that, how does that relate to clique? So here's a hint. You have a graph here. You have the graph here, and then we have the reverse graph here. Everywhere that there were edges here, there are not edges here. So for instance, this edge here does not exist here. But this edge exists here, but this edge doesn't exist here. Okay? We have the complement, the edge complement graph. What does this do? What does this show us? Well, let's look at the clique that the independent set that we saw before. Here, here, I don't know, here, here. And let's look at those same vertices here. Here, 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 here. What is this showing us? If this was an independent set here, then it's a clique on the reverse graph. Well, that's interesting, right? If something is an independent set on the original graph, then the complement graph, the edge complement graph, makes it into an independent set, or a clique, I should say. And that makes sense, because the two definitions are complementary, right? We're saying that one, the definition for independent set is vertices that are completely disconnected. And we're saying the definition for a clique are vertices that are completely connected. So, of course, if we do the edge complement of the graph, we could turn an independent set in graph X into a clique in graph Y. Right? So, what does our reduction look like? Well, what should our reduction look like? We want to draw the diagram. And I'm sorry, I have to draw it, we have to draw it in a small way here. But I will still draw it. So what does our reduction take? We have an algorithm, and we'll call this Y is clique, and X is independent set. Okay? So what does our algorithm for X look like? Well, it takes in a graph, and it takes in an integer k. And so what does the reduction do? It outputs a graph, the complement graph, edge complement graph, and the same integer k. And then if AY says, yes, there is a clique of size 4, of size k on the edge complement graph, then there must have been a clique of independent set of size k on the original graph. Right? So we just pass through the yeses and the nos. That's our reduction. Our reduction is simply taking the original graph and creating a new graph that only lists the complement edges. Okay? So that's what we've shown. This is just a proof for what we've shown. But so what does this show? This shows that independent set is polynomial time reducible to clique. Okay, so this means that if you have an algorithm for clique, then we have an algorithm for independent set. And clique is at least as hard as independent set. And in this particular case, independent set is also at least as hard as clique because the reduction could be reversed very simply. Okay, there is a reduction in the other way. But that's not always the case. You have to be very, very, very careful with this. So if you want to show that independent set is at least as hard as clique, then what do? We have to take the hard problem and then do a reduction to the unknown problem. Okay, and this right here, this polynomial time right here, sorry, I don't know why my pen is sorry, one sec. Okay. Let me pause the recording and I'll come right back. And we're back. Sorry about that. My Apple Pencil stopped working. Okay, so I want to show, if we want to show that the independent set is at least as hard as clique, we got to go from the known hard problem. If we want to show hardness, we got to go to known hard problem to the unknown problem. Okay, so doing both of those, we draw the reduction figure here. And then what do? We just fill out the blanks. Okay, so in this case, we have the input to the reduction is the complement graph, sure. And AX is clique, IY is the graph, AY is simply the independent set problem, and the reduction is simply calculating the complement graph. Okay, so this reduction diagram will be your best friend, at least until you become a master at reductions. Always draw out this reduction diagram because it'll tell you what you need to transform into what. And that's a huge, huge, huge boost. And it'll stop you from making the reduction in the wrong way. Okay, so assuming we solve the clique problem in T of n time, and I know that you can't necessarily solve it in this time. It's an NP complete problem, which we'll discuss in the next lecture. But assuming we do have a clique problem that you could solve in some T of n time, some linear time. Actually, we don't know T is linear. So actually, T might be exponential. That's fine. Okay, good. So how fast could we solve the independent set problem? According to what we said prior. Okay. And I'll give you a minute. Feel free to pause the video. Okay, so hopefully you worked it out, but the question is how much of the transformation from G to G complement, how big can it be? And so what's the biggest change that we could do from G to G complement? And I would say if G starts off with no edges, then G complement would end up fully connected with n squared edges, right? So really, the maximum, the upper bound for the reduction is n squared, and then we just input that new graph. The IY has increased. It went from 0 edges to n squared edges, so we input that new graph into the algorithm for y. So it would take E, O of n squared plus t of n squared time. Okay, so see you in the next one.